In this video, we're going to recap the gradient, curl, and divergence from multivariable calculus and how you integrate these things, and relevant theorems, which we use to relate integrals of gradients to integrals of functions, integrals of curls to integrals of vector fields, etc. So first we're going to start with the gradient. So the gradient, grad f, of a function from R3 to R. So I can actually define the gradient for functions from any manifold to R, but in exactly this way for any Euclidean space to R, but we're just going to stick to R3 for now, is defined by the property that if I take the dot product of the gradient of f with a vector, so it's the vector field defined by this property. If I take the dot product at any point with another vector field v, I get the vector field v applied to that function f at that point. So this means that, so this is the same thing as the directional derivative of f in the direction of v. This means that the gradient of f as a vector field is the same thing as the transpose of df, which is just the sharp of df. The transpose of df, this doesn't really make sense. This is just sort of a notational. So notationally, this is true, and this is actually how I can compute the gradient of f as the sharp of the exterior derivative of f, which is probably how you saw it in multivariable calculus. So it's a vector whose first component is df by dx, second component is df by dy, etc. So I can integrate vector fields over curves. So if C is a curve parameterized by gamma, which is a map from the interval AB to R3, then I can define the integral of the vector field f over the curve with respect to gamma. So I'm just going to use the notation integral over C of f dot d gamma. You might have seen something slightly differently in your textbooks on for multivariable calculus, but what this actually, because we're going to recast everything in the language of differential forms, this notation doesn't actually matter very much to us. Basically, the way you compute it is you integrate from A to B f at gamma of t dot gamma prime of t dt for a vector field on R3. And the fundamental theorem for line integrals tells me that if I integrate a gradient, not grad f, then this is the same thing as applying f at gamma of b and subtracting f at gamma of a. And so you can kind of think of this as sort of integrating f over the boundary of C, because integrating is really just adding. The boundary of C is really just 2 points, gamma of A and gamma of B. You can kind of think of the boundary of C as oriented by having a plus sign at the sort of higher endpoint, the point that's parameterized by the larger value in R, and then a minus sign at the point parameterized by the smaller value in R. Okay, so a similar story happens for curl. So there's an operator that sends vector fields to vector fields, and there is a similar kind of theorem called Stokes' theorem. So you might remember the curl of a vector field. So f, I'm going to write it as p d by dx plus q d by dy plus r d by dz on R3 is the vector field curl f, and I'm just going to write down how you can define it in coordinates. So this is dr dy minus dq dz d by dx plus dp dz minus dr dx d by dy plus dq dx minus dp dy d by dz. So it's some way of getting a vector field from another one. And on your homework, you're actually going to show that a sort of different formula for curl that will be sort of more, won't be written in coordinates. And the book actually gives you a geometric definition for curl using infinitesimal circulation of fluids. And we're not going to go into it, but if you are interested, you can read that part of the book. So just like integrating vector fields over lines, you can integrate vector fields over surfaces. So if S is an oriented surface parameterized by some map phi, which takes uv to x of u v, y of u v, z of u v in an orientation preserving manner. So the orientation d by du, d by dv gets sent to the orientation of S. If you have such a parameterized surface, then I can integrate, so it's parameterized by a UV region R via some map phi. Then I can cook up what's called the integral of F. So it's often some notation like this in multivariable calculus text. So basically you're just integrating your vector field over the surface. And I can integrate that by integrating over the region R, the parameterizing region R, F at the point phi of uv, and then dot that with the cross product of d phi du and d phi dv, and then integrate that du dv. This isn't a wedge product, right? This is just a normal double integral from multivariable calculus, for example. So Stokes' theorem is a theorem that relates the integrals of curls to the integral to line integrals. So if I have some surface S that's maybe some like blob in three-dimensional space, and then its orientation, so say it's got an orientation that's like the first vector goes that way, the second vector goes that way, then this determines an orientation on the boundary. So here it would be clockwise. So we're making kind of a lot of orientations when we're computing integrals over curves. They're also oriented, right? They're oriented by the direction of parameterization. Okay, so if I want to compute the integral over a surface of the curl of a function, or sorry, of a vector field, this is just the same thing as the integral over the boundary of the surface, oriented properly, of the original vector field as a line integral, so as one of these integrals here. So you can kind of see something going on. Yeah, so I'm basically relating the integral over some region to the integral over its boundary, kind of similar to what was going on in the fundamental theorem of line integrals, integral over a curve to some quote unquote integral over its boundary. So the final thing is the divergence. The final operator is the divergence. So this is of a vector field, again, is the function dp dx plus dq dy plus dr dz. This is some function from R to R3 to R, and it's denoted div f. Your book explains divergence geometrically using fluid flow, so you can read that if you're interested. And you can integrate functions over regions. We've talked about that already. And the divergence theorem tells us that if I'm integrating the divergence of a vector field over a region, then this is the same thing as integrating the original vector field over the boundary of that region. So say I have some ball, I can either integrate over the interior of the region if I'm integrating a divergence, or I can integrate over the sort of shell of the region. And I get the same thing. So the musical isomorphisms in the Hodge star are going to be used to relate the divergence theorem, Stokes theorem, and the fundamental theorem of line integrals back to the same theorem, which is called generalized Stokes theorem, which involves differential forms. And that'll be the subject of the next video.